Have you ever really stopped to think about how the device you're watching this on actually works? The whole journey starts with something you'd never expect: sand. In this explainer, we're going to pull back the curtain on the absolutely incredible process that turns that sand into the complex circuits powering our entire world. It's a process called lithography.
Okay, so this looks like something straight out of a sci-fi movie, right? But it's totally real. Welcome to the inside of a semiconductor fabrication plant, or a fab for short. This is one of the cleanest, most ridiculously controlled environments on the entire planet. And there's a good reason for that, because of what's happening in here. It's basically microscopic magic. This is where the building blocks of our digital world are born.
So that brings us to the big question. How on earth do we build these tiny cities of circuits with parts so small you could fit billions of them on your fingertip? How is that even possible? Well, the answer boils down to a process that is, at its heart, a hyper-advanced form of printing.
To really get our heads around this, let's just use a simple analogy. Imagine you're screen printing a t-shirt. You need three basic things, right? You need your shirt, that's the canvas. You need your ink, that's the paint. And you need the design, that's the stencil. Same idea here, just on an atomic scale.
So in our case, the canvas is this, a silicon wafer. And yeah, it really does start out as common sand. That sand gets purified and grown into a perfect crystal. Then it's sliced into these flawless, mirror-finished discs. This thing has to be unbelievably pure and perfectly flat because it's the foundation for, well, for everything.
Next up is our paint. This is a chemical called photoresist. It's a liquid that could spread in an incredibly thin, even layer all across the wafer. And here's its superpower. It's light sensitive. When a specific kind of light hits it, its chemical structure changes. That's the secret sauce right there.
And finally, we have our stencil. In the industry, they call this a mask or sometimes a reticle. It's a quartz plate with a ridiculously detailed pattern etched onto it. You can think of it as the master blueprint for just one single layer of the final computer chip.
So, we've got our canvas, our paint, and our stencil. Now it's time for the main event, actually printing the circuit. The whole process is called photolithography, which literally just means printing with light. And it all happens in 5 essential steps.
All right, here's the whole process at a glance. First, you coat the wafer. Then you expose it to light. You develop it, kind of like old-school camera film. Then you etch the pattern to make it permanent. And finally, you strip away all the leftover stuff. Coat, expose, develop, etch, strip. Now, let's zoom in on a couple of the most important parts.
The expose step is where things get really cool. A powerful ultraviolet light shines through the clear parts of the mask. That light then passes through this crazy complex system of lenses that shrink the entire pattern way, way down and focus it onto one small spot on the wafer. Then the machine just steps across the wafer, stamping that pattern over and over again until the whole surface is covered.
And this is what you get after that exposure and development. You go from the blank layer on the left to this incredibly precise foundation on the right. We've basically made a perfect temporary stencil, but this time it's sitting right on top of the wafer itself, all ready for the next critical step, making it permanent.
So, how do you make that pattern permanent? That's where etching comes in. They put the wafer into a chamber and they blast it with an ionized gas, a plasma. Just think of it like a microscopic sandblaster. It carves away at the wafer material, but, and this is the whole key, it only removes material from the areas that aren't protected by that hardened photoresist.
So once that etching is done, the photoresist, well, its job is over. It's what the sources call a sacrificial layer. Its only purpose was to take the hit during the etch. So it gets completely cleaned off, and what's left behind is the newly minted, permanent pattern that's now carved right into the wafer surface. And just like that, one layer is complete.
But here's the thing, and this is where it gets really wild. A modern computer chip isn't just one flat pattern. No way. It's a dense, three-dimensional structure. It's much more like a microscopic skyscraper than a single-story building. So how do we get from one flat layer to a complex 3D city? Well, the answer is surprisingly simple. You just do it all over again. And again, and again. That entire 5-step sequence we just walked through, it gets repeated dozens, sometimes hundreds of times. Each time with a totally different mask, laying down a new layer of material and etching a completely new pattern. And every single layer has to align with the one below it with almost impossible precision.
After all those repetitions, you get this. This is a cross-section of a finished chip. You can actually see all the different layers stacked on top of each other. It's a true microscopic city, all built one impossibly thin layer at a time.
So we've seen the incredible how.
But let's talk about the why. Why does this tiny, tiny process matter so much? Well, to put it simply, it's the foundation of our entire modern world. Every smartphone, every computer, every single server in the cloud, all of it depends on this remarkable ability to print with light.
To give you a sense of the scale we're talking about, the most advanced machines today use a technology called extreme ultraviolet, or EUV. The wavelength of that light is just 13.5 nanometers. To put that in perspective for you, that is smaller than most viruses. Think about that. We are literally sculpting matter with tools that are finer than nature's own nanomachines.
And you know, this technology doesn't just stand still. The push to make things smaller and faster means this field is always evolving. The optical lithography we've been talking about is the main workhorse, but scientists are constantly developing new methods, using electron beams, X-rays, even ion beams, to keep pushing the boundaries of what's even possible.
And the complexity is just staggering. This quote from our source at Micron Technology really brings it home. It says, a typical DRAM or NAND flow may have dozens of different masks. So what that means is, for a single memory chip, that whole 5-step process gets done dozens of times, each with its own unique, mind-bogglingly expensive mask, just to build up the final product.
So from sand to a silicon wafer, and from a beam of light to a city of circuits, lithography is the unsung hero of our digital age. But it leaves us with a huge, fascinating question. We're now building things so small that we're literally bumping up against the physical limits of atoms themselves. So as we reach the end of what's possible with printing with light, what comes next? What's going to be the next breakthrough that powers our future?